Hello everybody, it's a long time since we've done a wee lesson. I thought we would do another one here on the last bit of the electric fields, magnetic field stuff. This is applications of crossed electric and magnetic fields. Bit of a mouthful. Hey ho, there you go. Apologies for the state of my board. We're getting used then to seeing this sort of thing. Here's an electric field. A uniform electric field. This plate here is positively charged and this plate here is negatively charged. It's an electric field. And we've produced a potential difference across those two plates of say 5,000 volts. And the distance between those plates might be something like 8 centimetres, 0.08 metres. If we fire a wee electron in here, that electron is going to be deflected by the electric field between those two plates. Now the direction of the field lines always shows you the direction that a positive charge would move. A positive charge would be repelled down the way. So if I was drawing arrows on here to show the direction of the electric field's pointing downwards. But if an electron comes in, which way is it going to be deflected? Well, it's going to be repelled from the bottom plate and attracted to the top plate, and it will follow a parabolic path through the field there. Got a wee duster. So quite in the middle. Want it in the middle. This used to be how inkjet printers worked. Yeah. An inkjet printer used to spray little dots of ink through an electric field and then they would deflect them onto the paper and produce the letters on the paper. Before the days of laser printers and whatnot. Same with old televisions. In old television, the picture on the screen was produced by the deflection of an electron beam by electric magnetic fields. So an electron entering into that field at a particular speed will be deflected, and in this case it will be deflected up the way. Now, what happens if we put a magnetic field in as well? Now, the magnetic field is going to be crossed with the electric field. They're going to be perpendicular to each other. So I'm going to draw my magnetic field acting into the board. Remember, crosses indicate a magnetic field going into the board. Which way would my electron experience a force? What do we need? We need a right-hand rule. The right-hand rule tells us the direction of the force on a charge that's moving in a magnetic field. Crosses mean the magnetic field is going into the board. My second finger tells me the direction of the charge, left to right, and my thumb is pointing down the way. So the magnetic force on an electron in a magnetic field, or this magnetic field, that magnetic force will be downwards. So the electric force is attracting it up, the magnetic field is forcing it downwards. And what happens if both those forces are balanced? If both those forces are balanced, then that electron will travel through that field in an undeflected path. So if the forces are balanced, if the electric force is balanced with the magnetic force, we know equations for the electric force and magnetic force now. The electric force is produced by the electric field. Electric field strength is the force per unit charge. Remember that? Electric field strength is the force per unit charge. So F equals, it's a single electron, so let's make it Q times E. Yeah? But it's a single electron, usually the symbol for the charge is a small q. What about our magnetic force? Well, the magnetic force was QVB. We can substitute in for both of those forces. The electric force is QE, sorry. The magnetic force, QVB. What cancels out on both sides? The charge cancels out and we're left with E equals VB. Rearrange it and we get V equals E over B. And what does that equation tell us? That equation tells us that the ratio of the electric field strength to the magnetic field strength gives us a quantity that's measured in meters per second. It's a speed. The electric field strength, magnetic field strength, or the size of the magnetic field. That's in Tesla. That's in newtons per coulomb or volts per meter. When those forces are balanced, it will only let particles through with one particular velocity. I'll give you a wee example. Say that voltage was 5,000 and that distance there was 0.08. We could work out that electric field strength. Let's also say that we have, if we use a magnetic field or a magnetic force or a magnetic induction, if we put a magnetic field across that electric field and we've got a magnetic induction of 50 millitesla, calculate the velocity of an undeflected electron. So we want V equals E over B. Do we know what E is? No, but we can calculate it, because E, the electric field strength, is the potential difference divided by the distance. We've met that equation before. So 5,000 divided by 0.08, which is 62,500. Better get my calculator. I've got a calculator. Give me a minute. 5,000 divided by 0.08. 62,500. The electric field strength, 62,500 volts per meter or newtons per coulomb. And our magnetic field strength, or the size of our magnetic field, the magnetic induction is 50 millitesla. So 62,500 over 50 times 10 to the minus 3. And that will give us the velocity of an electron that passes through the field undeflected. Because of the velocity that it has, the magnetic force equals the electric force. 62 and 1.25 times 10 to 6. 1, 2, 3, yeah. Meters per second. And only electrons travelling at that speed will pass through undeflected. If they're going slower than that, well, if they're going slower than that, what would that affect? That would mean the magnetic force was less than the electric force. So the electric force would have more of an impact on it. So therefore, if it was going too slow, it would curve up the way. If it was going too fast, it would curve down the way. The magnetic force would be in favour the greater the velocity is. Only electrons travelling at that speed will travel through undeflected because of their velocity. Does it matter about the charge of the particle? Does it matter about the mass of the particle? Charge doesn't matter. We could quite easily fire in there any charged particle, any negative ion or positive ion. Charge cancels out. And there's no mass in that relationship at all. It's only the speed of the particle. So I didn't even have to say an electron there, I could have said a charged particle there. I'm going to show you the same thing again, but this time with a positive charge coming in. Remember, charge doesn't matter, mass doesn't matter. This is an alpha particle coming through here. An alpha particle is positively charged. it will be deflected by the electric field. It will be repelled by that negative plate and attracted down to that positive plate. It will move like that. It will go projectile path downwards due to the electric field. But the magnetic field, right hand rule, force going into the board, moving from left to right, my thumb's pointing down the way, but the right hand rule applies to a negative charge. That would be the force on a negative charge in a magnetic field, right hand rule. Force on an electron. The force on an alpha particle, a positive charge, would be in the opposite direction, upwards. So, the electric force is accelerating the charge, or exerting a force on the charge downwards. The magnetic force is exerting a force on the charge upwards. And when those forces are balanced, then that alpha particle will go through in an undeflected path. Now, there is only one velocity at which that will happen. V equals E over B. The size of the fields will be different, but the effects of the forces will be equal and opposite. Balanced forces will only happen at one particular velocity. And we worked out what that velocity was for our electron. It'll be the same. Remember, the electric field strength, E equals V over D. Doesn't matter that it's an alpha particle this time. The electric field is the same, the magnetic field is the same, so therefore the velocity of the particle has to be the same for it to pass through undeflected. Charge doesn't matter, mass doesn't matter. It doesn't even matter if it's positive or negative. Now, I've written the word mass spectrometer there. Go and ask Mrs. Casey if you do chemistry what a mass spectrometer is. She'll call it a mass spec. Mass spectrometers are used to determine the mass of individual ions. And if you can work out the mass of ions, you can work out the mass of atoms. And that's how they know the masses of all the elements in the periodic table, by using physics, by using a mass spectrometer. If that alpha particle goes through that magnetic and electric field, those crossed fields, then only one particular velocity of alpha particle will get straight through. If it's going too slow, if it's going too fast, it will be deflected and it won't pass straight through into this region where there is only a magnetic field of 50 millitesla. What will happen to that alpha particle when it passes through that field and it enters this region where there is only a magnetic field? Right hand rule, field's going into the board, charge is moving in that direction, negative charge would be forced down, positive charge would be forced up. It's going to move in a circular path when it enters the magnetic field. Now, if we know that distance, if we could measure the distance from there to there, that's the diameter of its circular path. And if that's the diameter of its circular path, we could work out the radius of its circular path. And from the radius of its circular path in the magnetic field, and we know its velocity, we can work out the mass of that charge. Watch this. In a magnetic field, it's moving in a circle, so the magnetic field acting on the charge must be producing this central force that's making it move in a circle. So QVB is equal to mv squared over r. We've been here before. Cancel one of the v's, rearrange it, and we get r equals mv over, did we say bq or qb? It doesn't really matter. qb. So if you measure that diameter, and then you can determine that radius, we could rearrange that equation even further. We could say m equals, let's get m on its own, m equals r q b over v. And if you know that radius of its circular path, you know what the charge on the alpha particle is. You know what the size of the magnetic field is. We chose that. You know how fast it's going because only one velocity of particle will get through our velocity selector. Then you can determine what the mass of that ion is, of that helium nucleus, of that atom, whatever, that charged particle. How does it separate charges out? How does it separate masses out if the masses are different? Well, if you had a slightly bigger particle, they're still moving at the same speed. Now, all the particles will be moving at the same speed because they have to be moving at a fixed speed to get through there undeflected. There's usually a little slit or something in here as well. A little slit that only allows the particles to get through a tiny wee narrow gap there. They've been undeflected. So they're all travelling at the same speed. So if they're all travelling at the same speed, they're all moving through the same magnetic field, they'll all get the same charge on them. Then if you have got a larger ion, it's got a bigger mass, it's going to have a bigger radius of curvature, a bigger radius of its circular path. A smaller ion, an ion with a smaller mass means a smaller radius. And so therefore different masses of ions will be separated out according to the spectrum of their masses. The mass spectrometer is used to determine the masses of different isotopes, of different elements.
Right, here's the slides that match what we've just gone over there across the electric and magnetic fields. If a magnetic field and an electric field are arranged perpendicular to each other, the electric force and the magnetic force on a moving charge can be balanced and the charge will move through the crossed fields undeflected at a steady speed in a straight line. So there's the diagram we had on the board. We've got a source of some charged particles. Originally this was done with alpha particles coming from a radioactive source, but those particles were fired into a field and the electric force acting on the charge was balanced by the magnetic force acting on the charge. Equal forces, opposite directions. Now that arrangement is called a velocity selector and it's used as part of larger systems where the properties of charged particles are determined. So if our magnetic field is into the page and if we fire a positive ion into the crossed magnetic and electric field, the magnetic field is upwards due to a right-hand rule. The electric force is downwards. And there's the relationships for the magnetic force, QVB, electric force, QE. And if we equate these, because when the forces are balanced, equal forces, opposite directions, QVB equals QE, the Q's cancel and we rearrange for V, V equals E over B. So by selecting particular values of your electric field and your magnetic field, you can select particles with specific velocities. So depending on the size of the electric and magnetic fields, only ions, charged particles with one specific velocity, will follow an undeflected path through the apparatus. Doesn't matter about the charge, doesn't matter about the mass, it's only the velocity that determines whether they will be undeflected as they pass through the fields. Right, here's a wee worked example of the velocity selector. Protons are fired from a source into a magnetic field and electric field that are perpendicular to each other. The magnetic induction is 115 millitesla and there's a potential difference of 2.5 kilovolts across the plates. The plates are separated by 0.1 meters. A part 1, calculate the electric field strength between the plates. Well, electric field strength is the potential difference across the uniform field divided by the distance between the plates. So 2500 divided by 0.1 gives us an electric field strength of 25,000 volts per meter. A part 2, calculate the force on the proton due to the electric field. Well, F equals QE and it's a proton, so its charge is 1.6 times 10 to minus 19 times that electric field strength gives us 4 times 10 to the minus 15 newtons. Part B, determine the speed of the proton if it passes through the apparatus undeflected. Well, we can calculate that speed because it's equal to the electric field strength divided by the magnetic induction. V equals E over B, 25,000 over 115 millitesla. Gives us 2.17 times 10 to the 5 meters per second. Then part C, an alpha particle is fired into the crossed fields. It's got twice the charge and 4 times the mass of the proton. State the velocity it must have to pass undeflected through the fields, and you must justify your answer. And must justify means you can't just have a guess, you have to explain why you're giving that answer. So if it's got twice the charge, 4 times the mass, do we need to bother about charge and mass? No, we don't, because remember this is independent. It only depends on the speed of the particle. So it must travel through at the same speed, 2.17 times 10 to the 5 meters per second, because the undeflected path is independent of mass or charge. The charge cancels out, mass isn't mentioned, it's just the velocity that determines whether it passes through in a steady speed in a straight line. There's our mass spectrometer. It's a better diagram than I had on the board. This is interest only, although you could be asked it in a kind of problem solving sense. So mass spec is used to measure a range of atomic masses of ions of an element. If those ions all have the same charge and they're all moving at the same velocity, they will pass undeflected through the first part of the apparatus, which is the velocity selector. And then when they enter into the magnetic field, they'll follow a circular path, and the radius of the circular path depends on the mass of the ions. And detectors can measure the relative abundance of different isotopes of the element. And there's our relationships for magnetic force and central force. If we equate them and rearrange, there's the relationship you would use to determine the radius of that curved path, and from that radius of the curved path you can work out the mass of the isotopes. One last thing is to mention the charge to mass ratio of an electron. We've already mentioned this, but it is another example of charges moving in magnetic fields. Remember, this was discovered by J.J. Thomson in 1897, and he was credited with the discovery of the electron. So if you fire that electron into a magnetic field, they get steered in a circular path, and the magnetic force provides a centripetal force. So there's the magnetic force equal to the centripetal force, equating them and rearranging for charge to mass ratio. Then if you know what the speed is, you know the magnetic induction and the radius of that curved path, you can work out the charge to mass ratio of the electron. The example at the bottom there, if an electron enters a magnetic field and it's going at 4.2 times 10 to the 7 meters per second, the magnetic induction is 9.3 times 10 to the minus 4 Tesla, and the radius is determined to be 0.26 meters. Calculate the charge to mass ratio for the electron. Works out to be 1.74 times 10 to the 11 coulombs per kilogram. That's applications then of charges moving in magnetic fields and electric fields. We'll see you in the next one.